Hello, honors pre-calculus students. Mr. Grisado here. Today's learning target is to talk about binomial probability. And there are four things that need to be true to be considered binomial probability. We're going to take a look at number one, and I'm going to explain those four things. So if you flip a coin 11 times, and the probability of tails is 0.6, what is the probability of getting exactly 3 tails? So this particular coin is not fair. If you look at number one, the first thing that you should notice is there are two outcomes. So for binomial probability, there needs to be two outcomes. In problem number one, tails or heads. The second thing is the probability of success is constant. What I mean by that in problem number one is the chance of getting tails is always 0.6. I'm going to call that a success for this particular problem. The third thing is the events are independent. What we mean by independent is if you flip the coin 3 or 4 times and you get tails, the next flip is not influenced by the previous flip. And then the third thing that needs to be, or the fourth thing that needs to be true for binomial probability is there is a fixed number of trials. So for this particular case, you're flipping the coin 11 times. So these are the four things to be that need to be true in order for it to be binomial probability. If you take a look at number one way students did this problem last year is we would draw 11 dashes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then underneath there they would say, all right, we need 3 tails. So they would put a T. And underneath the other ones, they would put H's. And they would realize, oh, I need 3 tails, so tails 0.6, 0.6, 0.6. The other ones are complements, so 0.4s. And they would realize, oh, I could just do 0.6 cubed, and then 0.4 to the 8th power. And they type that in, and then I would let them know that that's not quite correct. So what's missing? If you look at what I just highlighted, we're assuming there that the tails were all first. But maybe the tails were at the end. Or maybe it was tails, heads, etc. With just 3 tails. So how many ways can you rearrange those letters? This goes back to the previous unit of distinguishable permutations. So you have 11 letters. So 11 factorial over 3 factorial, 8 factorial. If you type that into your calculator, you will get the correct answer of around 0.0234. Now some students do this a different way. Some people would like to write the 11 factorial over 3 factorial, 8 factorial is 11 choose 3. So some people do it as 11 choose 3, 0.6 cubed, 0.4 to the 8th. And let's talk about why that's true. Off to the side, the definition of permutations n choose r was n factorial over n minus r factorial r factorial. So 11 choose 3 is 11 factorial over 8 factorial, 3 factorial. So hopefully that convinces you that the blue number and 11 choose 3 are the same. The way you could think about it is, out of the 11 spots, you want to choose 3 of them to be tails. And then some people would even say 11 choose 8 times 0.6 cubed, 0.4 to the 8th, because 11 choose 8 is also 11 factorial over 3 factorial, 8 factorial using the definition. And conceptually, out of the 11 spots, they want to choose any 8 of them. So whichever way resonates with you is how you should look at the problems. Let's take a look at problem number 2. In number 2, you roll the die 11 times. What is the probability of getting exactly 9 2s? So I'm going to start out with my 11 dashes again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I get a 2 9 times. and I don't get a 2 2 times. So I'm going to use n for no 2's. So that would be, and some people like to write it this way, 2 to the 9, or t to the 9, and then n squared. But then remember, you need the coefficient in front. So how many ways can you rearrange those letters? I'm going to say 11, choose 9. And then 11, choose 9. The chance of getting a 2 is 1 out of 6. The chance of not getting a 2 is 5 out of 6. And if you type that into your calculator, you're going to get a relatively small number. This is approximately 3.79 times 10 to the negative 6. Now, last year in class, I will tell you, people kind of put the 1 out of 6, 1 out of 6, dot, 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 1 out of 6, and then 5/6, 5/6, and then they said, oh, 1 out of 6 to the 9th, 5 out of 6 squared, and then they say, oh, how many ways can I rearrange those letters? 11 factorial over 9 factorial, 2 factorial. That number that I just wrote, here in highlighted in green, is equivalent to this number in blue. Let's take a look at problem number 3. In problem number 3, let's assume that the chance of a boy and a girl are equally likely. In a family of 12, you want exactly 2 girls. So I'm going to write girl to the power of 2, boy to the power of 10. I could use the dash method, but I want 2 girls and 10 boys. But remember, I need that coefficient out in front. How many ways can you rearrange these letters? So I like the combinations, so I'm going to say 12, choose 2. And then 12, choose 2. Chance of a girl, 0.5. Chance of a boy, 0.5. And then typing that into my calculator, you get approximately 0.0161. Go ahead and pause the screen and try problem number 4. Alright, so for problem number 4, you flip a coin 9 times, and you want to know the probability that you get exactly 6 tails, and let's assume equally likely. So for the tails, I want 6 of them. For the heads, then I would need 3 of them, but I need the coefficient in front, so that would be 9, choose 6. And then 9, choose 6. Chance of a tails is 0.5. Chance of a heads is 0.5. And typing that into the calculator, I'm going to get 0.1641. And I would just like to take the time to point out a pattern. Notice here in problem number 2, 11, choose 9. The 11 adds up to the 9 and 2. In problem 12, 2 and 10 add up to the 12. In problem 4, the 9 and 6, 6 and 3 add up to the 9. I'm going to go back to number 2. Notice for the 9, that's how many the exponent on the t. The exponent on the g is 2. And in 9, choose 6, that's the exponent in the t. So there's a little pattern here. Okay. Why don't we take a look at problem number 5. Go ahead and try to pause the screen and try that problem. Alright, so in problem number 5, you want at most 1 4. So at most 1 4 means you get 1 4, 2 4s, 3, 4, 5, 6, or 7 4s. And in the previous unit, we talked about when you see the word at least or at most, you might be thinking of complement. So if you look at what I wrote here, what's missing is 0 4s. So it might be easier to figure out the probability of getting no 4s and then doing the complement. So I would suggest you figure out the probability of no 4s and then do 1 minus that. So 1 minus the probability of no 4s. So what's the probability of getting no 4s? So that would mean they're all non-4s. So if I were to write that down, it'd be like 4 to the 0 and then non-4s to the 7th. And then in front of that, I would need 7 choose 0. So 1 minus 7 choose 0. The chance of getting a 4 is 1 out of 6. The chance of not getting a 4 is 5 out of 6. And that would be the 7th power. And then when you type this into your calculator, you get around 0.2791. So this is approximately 1 minus 0.2791. And let me fix that. So the final answer here is 0.7209. So the other way you could do this is you could say, for instance, do the chance of getting 5 4s. So that would be 4 to the 5th, not getting a 4 2 times, and in front you'd have to do 7 choose 5, which would be 7 choose 5. Getting a 4 is 1 out of 6. Not getting a 4 is 5 out of 6. So if you wanted to do it, you could figure out this blue number that I just calculated. Then you would have to repeat that for getting 6 4s, 7 4s, 4 4s, 3 4s, 2 4s, and 1 4. And you would have to add up all of those numbers. But it's a little more efficient to calculate no 4s and then do 1 minus that. All right, problem number 6. On a multiple choice test, let's say that Mr. Fay, Mr. Moretti, or your social studies teacher gives you. The test has 60 problems on it. What is the probability of getting 40%? This means exactly 40%. Let's assume you did not study for the test at all. So getting a 40%, and if there are 60 questions, that means you got 24 correct. And if you got 24 correct, that would mean you got 36 incorrect. So what does that mean? I want 24 correct. Incorrect, I would want 36. And then the combination in front of that would be 60 choose 24. So 60 choose 24. If there were 5 choices, the chance of getting it correct would be 1/5 or 0.2. Incorrect would be 4/5 or 0.8. And when you type that number in your calculator, you get a relatively small number, 0.0002. So for problem number 7, hopefully you paused the screen and tried this problem. You want a 60%. So for correct, since there are 60 questions, 100 questions, and you want a 60, so you would get 60 correct. And then for incorrect, you would get 40. So in front of that, it would be 100 choose 60. And then there are still 5 choices. So this would be 0.2 to the 60th, 0.8 to the 40th. If there were only 4 choices, it'd be 0.25 and 0.75. And doing this on your calculator, you get a relatively small number, 2.106 times 10 to the negative 18th. Now the real question is, what's the probability that you get a passing grade? And that's a little more complicated. You can learn that in statistics, but if you didn't study, the chances of getting a passing grade are relatively small if you do the mathematics. All right, the last 2 problems have a similar idea. So go ahead and take a minute to read problem number 8. So for problem number 8, we want to choose 3 desert sand. So I'm going to say D cubed. 3 royal blue. So I'm going to say R cubed. And 10 indigo. So I'll say I to the 10th. Now an important word here is with replacement. And the reason that's important is then the events are independent and the probability doesn't change. So what are the chances of getting a desert sand? 7 out of 34. That's this 7 right there. The chance of getting a royal blue, 8 out of 34. And because I'm always putting the marble back, I can do that. And then the chance of getting an indigo would be 19 out of 34. And that was to the 10th. Now, how many ways can you rearrange those letters? Well, in this particular case, there are 16 letters. You get that by doing 3 plus 3 plus 10, so 16 factorial over 3 factorial, 3 factorial, 10 factorial. So for the D's, R's, and I's, that's how many ways you could rearrange them. So doing that on your calculator, you get approximately 0.0541. Pause the screen and try problem number 9. So for problem number 9, we want 3 desert sands, so I'll say D cubed again. 9 royal blue, so I'll say R to the 9th. And 3 indigos. Again, key word there, with replacement. So the chance of getting a desert sand is 7 out of 42. That's this 7 out of the total 42. Chance of a royal blue, 25 out of 42. And indigo, 10 out of 42. And I forgot to write the exponent, so it would be 7 out of 42 cubed, 25 out of 24 to the 9th, 10 out of 42 cubed. But then you need to ask yourself, how many ways can you rearrange those letters? So right now it looks like we have 15 letters, so 15 factorial over 3 factorial, 9 factorial, 3 factorial. And typing that into your calculator is about 0.0587. So this is a short introduction to binomial probability. If you take statistics next year, or your senior year, or in college, you will also talk about binomial probability.